So when we are done with chapter 2, at that point I'll announce what the quiz for chapter 2 and the master set for chapter 2 are. That's the way it generally works. That's basically the pattern. It's a 16-week course, so a lot of in-class quizzes. And also the master sets will count. So you can start on the master set before we're finished with the chapter. You don't have to have the due date. But some of the questions you might get to and go, well, we haven't done this yet. And that's fine. We'll eventually get there. Or if I say I'm officially done with chapter 2 and I haven't covered something that's in the master set, just ask. The large majority of the questions on a master set, especially on 2 through 5, are open test questions. As a side note. So when we're done with chapter 2, I will go over to the handy dandy charts over there and write down when things are actually due, not when Blackboard says it's due. Lose. Look.
KB approved.
KB. And then Caroline. Yes. Okay. Most of them right so far. And I want to say Johanny. Yes. Okay. Well, better than a week ago. So, Luz, Priscilla, Kiara, Christina. Good. Any questions? Yes, Jeff.
As for the master sets, are they in the book? I just didn't know.
The master sets are posted online.
Okay.
So you'd go under the course, module 1, chapter 2, and somewhere down there that should say master set chapter 2 or master set, something covered like that.
Okay. That's-
Chapter 10, that's fine. For you. Let's see, we did box on ramp. I think we finished box on ramp. All right, it's time for box on ramp on Earth. Before the ramp was part of the planet, now I'm making the ramp separate. Or I guess I was using ground before, on ground. And it might look like I'm trying to put a curvature to the planet, but I'm not. It's supposed to be a straight line. All right, so we start out by drawing the 3 separate objects there. So I've got the box, I have the ramp, I have the planet, and my checklist. So, let's start out with the easy one, at least what I consider the easiest, weight. Weight is acting on what objects and in which direction?
The box on the ramp, and then the ramp going up towards the box, and then the box going down the ramp.
So, down on the box, up on the ramp? Is that what you're saying? Or
No, that way.
that way, all right.
Or,
There's a slight problem with that. If I have the ramp, if I were talking about weight, gravitational force, if that ramp just magically disappeared, would the box, because it no longer has the ramp there, would the box just hover?
no,
So there's something else pulling on the box, not the ramp. What causes weight
gravity.
from? It is a force.
Friction?
What object? All forces require two objects. One object is the box. What's the other object involved in weight? Not the ramp.
The ground.
Yeah, it's the planet. Planet's causing it. If the ramp disappeared, the box is gonna fall because the planet is still there. If the planet disappeared, well, the box wouldn't have the weight on it anymore. So it goes down on the box, up on the planet. Because I do have more than one small object here, I do need to use subscripts, and so I'm just gonna use something cover like B for box. And Christina.
Mm-hmm.
All right,
And then you got ramp and,
pardon?
ramp and a planet
Okay, which way is it acting on the ramp?
down, planet up.
Now, if you don't want to use R for ramp and B for box, that's fine, just so long as these two have the same subscript, these two have the same subscript. All right, that's it, those are the two small objects, weight is done. Oh, is there anything we can get rid of? Okay,
Other,
yep, those are the two. So that leaves friction and normal force. Now, some of you might be thinking friction's easy, but let's just do normal force next, just because we do have a slightly different twist on friction here. Normal force, acting on what object and in which direction?
Acting on the box from the ramp at an angle.
And where's the other part of that pair?
ramp,
It's going angled on the ramp. Not the way.
Any other normal forces?
Ramp and ground.
Anywhere they got objects touching. So which way is it acting on the ramp? I saw gestures, someone said down, they said it too quietly. So, why some R and why some
because they go opposite.
I have only two places where there's contact, and so that's, like, so I have two pairs. And now friction. Friction does require that there be a normal force there, so wherever I have a normal force pair, I need to consider friction. If there's no normal force pair at an interface, then there cannot be friction. So, I got a normal force pair here. Which way would friction be acting on the box?
To the right.
So friction's helping the box go down the ramp?
That's up the ramp.
Okay, it's either up or down, it's one of those two.
It's up.
Another vote for up, there seems to be a groundswell here. Relative to the ramp, the box wants to go that way, therefore friction says no. Ramp says, I'm gonna try to stop you. That's my friction there. And the other part of that pair?
Gravity.
On the right?
That's a different pair. Forces come in pairs, so
On the left.
down where?
Along the slope of the, along the slope of the ramp.
Yeah, so not down that way, but down the ramp. we have another pair of frictions. We have another pair of normal forces, so we need to at least consider friction in the other spot. Yep.
On the rail?
Now, which way is it going on the ramp? If the ground were frictionless, if this were a frictionless surface, which way would the ramp move? Jason, what were you saying?
No way.
It would go somewhere. If this were frictionless, the ramp definitely would go somewhere.
Is it backwards?
That way?
Yeah.
Going with the finger gesture?
Yes.
Yeah, it's like, I have something caught between two objects, and one object is pushing down on this, so it's trying to squeeze it. Basically, it's trying to squirt this thing out that way. So there's friction acting this way on the ramp, and the other part of that pair, yeah, and it's also a gesture to the left. So there's your complete force diagram. And for completeness. Questions? All right, so now, I think I postponed nitpicking the term gravity before, so I'm gonna go ahead and talk about that for just a moment. Weight, first off, weight is a type of gravitational force. Gravity is a huge topic. There's curvature of space and time because of gravity. There's acceleration due to gravity. There is the gravitational constant. There is gravitational force. There's all different gravitational field. There's all sorts of different aspects of gravity. So when you say the word gravity, you're referring to a very large topic. When you're talking about the forces, you're talking about a very small part of that. So when you refer to weight or the force, weight is fine, force due to gravity is fine, but there are three things that students in this class tend to all call gravity when they are different things. There's the acceleration due to gravity, force due to gravity, and the gravitational constant, of which we've really only talked about one in any minor detail. They are all different, they should not be given all the same label. So, if I say what force is acting on it, and you say gravity, again, you were talking about a huge topic, be specific, force due to gravity, or, in this case, weight. Now I get to nitpick. Any questions? Sorry, this didn't I? All right, so at this point, we've talked about friction, weight, normal force, obviously, time to do tension. Christina?
You might have to turn it a little because it's cutting off half the board.
I'm really close to the edge there. I think it's picking up almost all of it, unless I draw at the very edges.
Okay, you want corner is a corner. Okay, got you.
Would you like me to back it up?
You're good.
Okay. Just trying to prepare you for the business world where expect technology to go wrong. So tension, let's bring some tension into it. So we'll start out with a simple two-box dangly. I'll probably call this mass 1 and mass 2. At this point, we don't want to bring in too much reality yet. The more and more reality we bring into it, the much more it gets very complicated very quickly. So we have to, so in essence, you start out with the simple examples, and then in physics, the typical trend is you start adding a little bit more reality, And eventually you get to the point where you stop using numbers completely and it's all theoretical. We will not get that far. And I know it'll make some of you sad, but we won't get that far. All right, so this rope is what I refer to as an ideal rope. The Sasson refers to it as a magic rope. Either one works. Ideal rope has a couple characteristics. Number one, it is massless, which means it has no weight. It is stretchless, which means if two masses are connected to the same rope, if one object moves away, the other object will move with it. So I'm not going to have a situation where two is going to start falling and one is just sitting there. They will move together. And it is frictionless, except potentially where it's touching. The masses itself, we assume it is affixed to the masses, but it is not going to cause this pulley to turn. The pulley is also ideal. It is massless and frictionless. So we're going to start out, the pulley's not going to turn at all. In 151 and 251, we eventually do away with the massless, frictionless restriction. We get away from the ideal pulley. And in the rope in 251, we get away from actually we had friction in 151, 251, and massless we sometimes get rid of in 251, just to give you some idea of, in further physics, how is that different from what you're doing. We tend to keep the ideal here. All right, so let's draw the masses. I got one, I have my rope, I have two, I have the ground, and now there's the question of that pulley. In the test level problem, I will split it up for you. I'll present the problem, I'll give you the picture with everything attached to it, and then I will give you the problem with everything separated. Because it takes a while to get used to how do you want it split up, especially the more complex problems. So I would draw the pulley as part of the earth attached to the ground to indicate that this is all one object. Forces between the pulley and the ground we are ignoring because it would be considered an internal force. By the same token as we are ignoring the forces from the top part of the box to the bottom part of the box. So this is one object. Any forces within it are considered internal forces and are ignored. In essence, they cancel each other out. And then, so first off, can we get rid of anything?
Other.
And that's it. So let's start with weight. We'll end with tension since that is the new one. So weight.
Down on both boxes. Down on both boxes.
Okay. And that's the subscript because I got two of these things. However, that's only half the problem or half the answer. Where's the other?
From the ground.
On the ground. W2, W1. Now the ground is this whole thing right here. You could put the two weights right next to each other from a analysis point of view, it doesn't matter. I tend to put it underneath where the other one is, just so I'm keeping track mentally. In a more complex problem where I've got 5 or 6 different things, it might make it a little bit easier just to keep it sort of lined up. All right, weight is done. Normal force.
Up on box one.
Down on the ground on box one.
Wait, say that again?
Down on the ground on box one.
Okay. Okay, so on the ground. Y1. All right, so there's that pair. We have one other pair of normal forces.
Same thing to box 2.
What is box 2 touching? Is box 2 touching the ground? Is it touching the cliff?
It's touching the road.
Yeah, it's touching the rope, so we do have a force between the rope and mast 2. That's what we're gonna call tension. So, but there is no normal force acting on mast 2.
So if there's two objects touching, but one of them is, but they're tension, that does not mean they're normal force.
Right, because in reality, we don't know how the rope is attached to box 2. It is possible that it is being held there by a normal force, in which case, so if I have an eye hook and it's tied to the eye hook, there would be a normal force on the rope. Or maybe that it's just fixed in there and there's a friction force. We don't know how the rope is attached, and so we're gonna lump that into tension. There's a video that I did saying tension does not exist, I think, something like that, which goes into more detail.
Is it the pulley that's on the ground and the rope?
Yes, they are touching. There is a normal force there. I did not give you enough information to know the exact direction, but I do know that it's going somewhere in that direction. It's gonna be anywhere from, well, it touches here to here, so it's gonna be somewhere in that region right there. I just generically draw one, and I'm gonna call this R for rope, and then one back this way, Y sub R. X sub R. Now, some people get the normal force on the rope in the wrong direction. Well, they do that for a lot of things, but just remember there's something causing that rope to bend. So it's that normal force which is causing it to bend. That's it. So normal force done. Friction.
Backwards on box 1.